Hey everyone, this is Bhargav Suthar, and today we are continuing with the topic what is a Boolean algebra. So basically, this is the part 2 of Boolean algebra, and in this session, we will discuss some more examples of Boolean algebra. So let us recall what is a Boolean algebra. It is a lattice that is a less than or equals to is known as a Boolean algebra or a Boolean lattice. If it is both, it has to be first complemented and second the distributive. Now these are the properties, or note that first it lattice, and that means if it is a Boolean algebra, then the lattice should contain 2 raised to n elements. This is actually a result. So whatever the Hayes diagram will be, it should contain the 2 raised to n elements, and obviously n is greater than or equals to 0. Now a lattice contains a greatest element and a least element. It should contain a greatest element as well as a least element. Now let us discuss some more examples. Now determine whether the following Hayes diagram represent Boolean algebra. So we will have, see, the first Hayes diagram is like this, the straight line 1, 2, 3 and 4. The second diagram, it is like this cube but some additional points. And the third one is like this, it is the cube but something different. Now first, let us consider this graph, the first one. Now to check the Boolean algebra, all we need to check it has to be a complemented and a distributive. But it has to be a complemented and distributive lattice. So first it has to be a lattice. So for lattice, we will have to create the GLB table and LUB table. So let us create it. So the GLB table will contain here how many points are there? 1, 2, 3 and 4. Now these 4 points are there, and that is 2 raised to 2. So that satisfies that property. So we can go further. Now the points will be like this: 1, 2, 3 and 4. The naming, and in column it will be 1, 2, 3 and 4. Now 1 and 1. So least upper bound of 1 and 1, it will be 1 as the point is same. Now 1 and 2. So this 1 and 2. The upper bound, so this will be 2. So that is 2. Now 1 and this 3. The least upper bound, it will be 3. And last, this 1 and 4. So it will be 4. So that means 4. Now next, 2 and 1. So 2 and 1. So it will be 2. Now 2 and 2. It will be also 2 because it is the same number. Now 2 and 3. So 2 and 3. The least upper bound, that is 3. So here the answer will be 3. Now 2 and 4. So 2 and 4. The upper bound, so that will be 4. Now 3 and 1. This 3 and 1. So it will be upper bound, so it will be 3. And then 3 and 2. This 3 and 2. So obviously it will be 3. And again it will be 3. Then 3 and 4. So it will be 4 because it is in upper and the least one. Now 4 and 1. What was there in 1 and 4? It was 4. So here it will be 4. Now 4 and 2. What was there in 2 and 4? It is 4. So here it will be 4. Now 4 and 3. What was there in 3 and 4? So 4. It is 4. And 4 and 4. So it will be 4. Now you can see that this 4, it is the greatest element in the Hayes diagram. So this row and this column will be 4. Now in same manner we can create the GLB. So the points are 1, 2, 3 and 4. And again in column it will be 1, 2, 3 and 4. Now greatest lower bound of 1 and 1, it will be 1. Now 1 and 2, 1 and 2, lower bound, it will be 1. Now see, this 1 is the lower bound or the lowest point of the Hayes diagram. Okay, so in this whole row, it will be 1. See, now next 2 and 1. So what was there in 1 and 2? 1. So it will be 1. Now 2 and 2, it is same point to 2. So 2. Now 2 and 3. So 2 and 3, the least one, so that is 2. Now 2 and 4, 2 and 4, so 2. Now 3 and 1, it will be 1. Now 3, I'm just directly doing it. Now 3 and 2, 3 and 2, it is 2. Now 3 and 3, both are same, so 3. Now 3 and 4, the least one is 3, so it will be 3. Now 4. Now see, 4 is the highest number and we are trying to find the greatest but the lower bound. So all, because see, with respect to 4, all are the lower bounds and the least one. So here it will be 1, it will be 2, it will be 3, and 4 and 4, so it will be 4. So you can see that we've got all the GLB and LUB for each and every pair. So every pair or subset has GLB and LUB. So at least we can say that it is a lattice. So it is a lattice. Now we will check whether it is complemented or distributive or not. So A has a least element. How? So again, I'm just doing just one. We have this Hayes diagram. 1, 2, 3, and 4. So see, this 4 is the greatest element and this 1 is the least element. And we are calling this least element as O and 4 as I. So least element is 1 and greatest element is 4. And the number of elements, we have the number of elements and we can say that it can be represented as 2 raised to 2. So that property satisfies. Now let us check for the complement. Here, let's see. Here every element does not have a complement. Let us check how. Now I'm drawing the Hayes diagram. One, that is 1, 2, 3, and 4. Now see, 2 and 1, the least upper bound of 2 and 1. See, 2 and 1, the least upper bound, it is 2. Now 2 and 1's greatest lower bound, so it is 1. So this is 2 and this is 1. Now in same manner 2 and 3. So 2 and 3. This 2 and 3. The least one is 2 and it is the greatest one is 3. And now 2 and 4. So that means this 2 and 4. So the 4 and 2. But see, for complemented lattice, this answer, all the answers should be either the greatest element or the least element. But you can see that here it is not the greatest element. Again, here it is not 4 or 1, and also here it is 4, but here it is not 1. So this cannot be a complemented lattice. So A is not a complemented lattice as 2 does not have complement. So hence this lattice is not a Boolean algebra. So no need to check for the distributive. Now let us consider the second one. This was the graph. First, just whenever the question is given, just check the number of points. Just count the number of points. How many points are there? So I think 3, 3, 6, 7, 8, 9, 10. So here 10 points are there. Here we have 10 points. Just correct it. We have 10 points. But we can say that now we cannot represent 10 as 2 raised to something. So this directly, it is not a Boolean algebra. So, if it is asked in more marks, so you will have to check all those conditions, all those tables and stuff. But just by looking at this, just by counting the number of elements, you will get the idea it is not a Boolean algebra. Okay. So it is not a Boolean algebra. Now let the last one. This is the graph. Now this is the different one. Now see, there is no GL for the pairs this. Now let us discuss how. Now see, A and C. Just consider these points A and C. So what will be the least greatest lower bound of A and C? Greatest, and it has to be a lower bound. Now see, for lower bound there has to be a relation from the lower points to the given set. So just consider this pair A and C. Now can we go from A to C? We can go from A to B and B to F, but see, the C is not connected to F. So we cannot get the relation. So AC does not have the GLB. Now in same manner, just consider B and C. Just consider B and the C. Now in same manner, B and C are not connected. So again, B and C won't have the greatest lower bound. And in same manner, CD. The C and D. The C and D. So that they are not connected as well. So C and D that won't have the lower bound, the greatest one or the low. And in same manner, the C and F they are not also connected. So C and F that does not have the lower bound. So hence it is not a lattice or it does not represent lattice. So hence it is not a Boolean algebra. Thank you.